as a reminder, what we're trying to do is find a replacement for these basic ratio equations that ultimately we do find in various forms quite a bit throughout physics in the form of assumption. You'll find this everywhere in physics. And so basically, it's apparent that this limitation is ultimately related to the concept of absolute space, because this does not take into account infinite relative frames of reference as we have been pursuing. So what the question is okay, how do we modify these so that they do take these infinite relative frames of reference into account, so that we can then replace them, apply the replacement to special and general relativity, as well as modifying the definition of acceleration, seeing what that does, and to ultimately see if anything happens, and can we account for the apparent anomalies in a lot of modern physics experiments. Back to the relative frames of reference. Before, if you recall, I showed these, and that there were four: this relative to A, this relative to B, this relative to A, and this relative to B. But as it turns out, those two are, that set of two and that set of two are more or less mathematically equivalent, in the sense that though the frames of reference are not equivalent, the ratios that we're seeking are. So you only need one set of mathematics where two would go, because the one satisfies the need for both. So that's why we only need to focus on these two series of relative frames of reference. So if we look, let's start with, since this one's closest to us, we have B relative to A. Well, where do we find that here? Well, to our previous example, this equaled 0.2, this equaled 5. The ratio of B to A was 1 to 5. So that for every 5 minutes A experiences, B experiences 1 minute, or for every 0.2 minutes B experiences, A experiences 1 minute. And the units don't matter here, because it's the issue of the infinite frames of reference and how to account for that. So this ends up becoming a unitless mathematics, but that's because what you do is you apply the units to this once you've done it. Very similar to how the Lorentz transformation equation is. If you look at that, it essentially is unitless until you apply the speed of light to it. So that's how this ends up being. Okay, so this ratio could be associated with B relative to A, B relative to A for this many units of B. That's what A experiences, and this could be A relative to B. So how do we account for A relative to B relative to A, etc.? Well, one way of doing it is, what if we were to just add another, oops, sorry about that. Let's go ahead and clean this up a little bit. What if we're going to just add another A over B? You know, we're just going to add a little bit to A to account for at least one additional set of relative frames of reference. And the way to think of that is going back to our little reference frame boxes here. We'll let this be A relative to A relative to B relative to A, B relative to B. So in this box, that would be where we have the ratio of B over A. And in this box, this is where we would have the ratio of A over B. But then there's the implied fact that A relative to A and A relative to B have a variance between them, and that these variances leading from A relative to A to A relative to B and B relative to B to B relative to A, such that what we're doing is mapping out their displacement relative to each other in relation to time. So this is a mathematics that evolves around the concept of there being a variance in time as we progress from one state to the next. So the first one would be A over B. So the next set of frames of reference then would be A over B plus A over B. And over here, we'll just go ahead and take a little away. Oops. And so this would be B over A minus B over A. And so what you can see is that, we'll go ahead and change this up a little bit here. But what's going on is that we've got A over B plus A over B, which is more or less is N. So we have a plus N equals N prime. Well, and because this continues, this becomes N prime, and this becomes N double prime, this becomes N double prime, this becomes N triple prime, and it just keeps going, because that just keeps going. So ultimately, what we're dealing with here is a continued fraction. And so we have A over B plus A over B plus A over B, and that just keeps going, and that this equals N star. And so the way we do that for B then would be B over A minus B over A minus B over A, that equaling U star. And because we're dealing with infinite frames of reference, because A over B does not equal 1, we can't use N times U equals 1. So what we replace this with is, and we replace 1 with a value that we'll call the identity constant, or I, and I, the identity constant, is greater than or equal to 1, because if I equals 1, then that actually would mean that A and B are equal, and that, so this way, if A and B are equal, the identity constant's 1. If A and B are not equal, the identity constant's greater than 1 because of the predominance of A over B. And the reason why we do that becomes more apparent later. And the way we derive I is simply n star times u star equals I. So what we have here is this is an infinite progression, this is an infinite regression to account for the infinite relative frames of reference and how they're interwoven and interrelated as a replacement for the concept of absolute space. A good analogy for that is to think of this when I put this mirror up here, and you can see this continuous, I hope I'm getting that, but this continuous repetition of the image within the image within the image, so on and so forth, that represents, sort of as an analogy, what we're talking about here as a series of infinite frames of reference within frames of reference. And so for A, since A is older and more towards the future, we have a progression, and because B is in the past, relative to A, we have a regression. And so what should be pretty apparent to anyone that understands or knows special and general relativity is that, or even quantum mechanics, is that the places where this really is going to go in and deal with the issue is going to be concerning the Kronecker delta, and the Lorentz transformation in both relativity. Also in quantum mechanics, this is going to deal with the Hamiltonian and it being a Hermitian operator that's unitary, and this gets right in there. As a reminder, you'll hear me referring to A being older than B, B being younger, and me referring to this relative frames of reference having to do with that. Me using A and B being older and younger is simply an analogy, because the way I came to this was through that conversation with my great-grandmother, and that since she was saying time was going by faster for her than it seemed to be going by for me, it made me think, okay, what's going on here? And ultimately, the only way I resolved it was that she must be experiencing a completely different, what I can now say, objective frame of reference than I am. If we're both looking at the lawn and she's seeing the grass growing and I'm not. So to account for that, this is the complex mathematics that was needed. And so this isn't something just for applying to the subjective human sense of the passage of time. The mathematics that kind of comes from this applies to special and general relativity in this way. In Einstein's concept of the curvature of space-time, if we do have individuals or clocks having time pass at different rates, whether they're observers or just a clock ticking, a non-sentient being, an inanimate object, that we still have to apply these modifications to the ratio, going away from this to account for infinite frames of reference, if we're going to use a model that assumes infinite relative frames of reference, which personally I think is needed in special and general relativity. And I find that by applying it there, some of the strange anomalies that are occurring when trying to understand the data in experiments, specifically in astronomy, that some of that strangeness can be, or those anomalies can be accounted for by just simply applying the concept of of infinite relative frames of reference, the mathematics that comes from that, and moving forward. So I just wanted to point out that distinction, that though there is a mind-body philosophical consciousness, psychological aspect to some of this existics material, that the mathematics that we're deriving and dealing with right now really go more into applications in special general relativity and re-examining the way that acceleration is defined and carried out mathematically in basic Newtonian physics. Given that whether we cover up this part of this continued fraction or this part, or the same for this, that we can get the same value in the same way, we can let this go to u star and this go to n star. And what's nice about that is, even before we go ahead and solve for u star and n star, what we can see is it looks like we're going to go ahead and be able to avoid the issue of this running off to infinity and this basically just converging to zero, so that our relative frame of reference mathematics either becomes meaningless by becoming infinite or zero or nothing. So what's nice here is it looks like what's emerging is that we are going to be able to use the concept of infinite relative frames of reference, a more Leibniz interactionism based model, and applying that to physics, and again using the ratio n star times u star equaling I, the identity constant, where I is greater than or equal to 1, in situations where the mathematics, such as n times u equaling 1, this in general, in special relativity, this would apply to the Kronecker delta, and the Lorentz transformation in quantum mechanics, this would apply to the Hamiltonian, being a Hermitian operator and being unitary. So basically what it boils down to is, okay, now we're going to be able to derive some real mathematics that we can now apply a concept of relative frames of reference with an infinite series of infinite regress, and apply that to the modern physics equations and see if in any way it can account for some of these so-called anomalies that they're finding in their data with the experiments. Let's go ahead and solve for n star. And what we can do is go ahead and multiply over b, so we end up with n star times b. So this goes away. Now we can subtract over the other n star. So that goes away. Now we can factor out the n star. What that leaves us, and then we can divide this back over. And so basically what that tells us is that n star equals a over b minus 1. Obviously we're going to put the restriction that b must be greater than 1. What's interesting is that as you try various, as you apply the existics equations and try various problems, what you'll find is that when you get into really distant relative frames of reference, say the experience of time of a black hole versus some person hanging out on the moon, this problem gets a little bit more interesting, to where the resolution around the problem becomes the application of intermediary frames of reference. You can find the concept of intermediary frames of reference fully developed in the Existics 101 PDF on the Existics 101 website, or just Google Existics 101 and look for a PDF and you'll find in there intermediary frames of reference. What's cool about the intermediary frames of reference is that the age analogy has that, because the assumption is that time, that the passage of the rate of time increases with age, that we actually have to account for the variation constantly changing over time. So not only do we have a variance between one time to the next to account for, but that variance is varying. And so the use of intermediary frames of reference is handy in that, because as it turns out, what we end up with is a need for a maximum and a minimum number of frames of reference, and then when you integrate over that, that's how you solve for those curves. That has serious application in general relativity, and again, that is intermediary frames of reference. Okay, so since going back to what we were doing, let's go ahead and solve for U asterisk or U star. And so let's go ahead and, since we have that, let's just go ahead and make some room. Just go ahead and clear it. Let's just rewrite this out. So what we'll find is more or less a similar thing. We multiply the A over, then we subtract the U star, or I'm sorry, we add the U star this time. We factor out the U star, and we divide over A plus 1, and we end up with B over A plus 1 equals U star. So now we solved for U star, and again I want to put some emphasis on the elegance and simplicity of what we've done, because it seems that there was a lot of unnecessary hype and fear over using the concept of infinite relative frames of reference in a more interactionism-based calculus, which was suggested by Leibniz. And because these obviously can converge quite often and frequently to finite values. So even though this comes from a continued fraction that completely openly expresses the idea of infinite relative frames of reference, this accounts for it now, but doesn't have the, we don't have to stare at infinity every time we're doing these calculations. So this is quite interesting. And again, what we have is n star times U star equaling the identity constant. So now that we have solved for n star and U star in the identity constant, let's go ahead and derive the proper equations for finding where A and B are relative to one another. And they're actually really quite simple. Just as a reminder real quick, when A over B equal each other, hence the identity constant is 1, if we were to want to find A star, which is the modification of A, so this would be the A that's slightly into the future relative to A, that what we would do in this situation is we would actually be adding n, which in this case would also equal 1, because that equals 1. So we have n minus 1 being the identity constant, so that those would be the same, so that there isn't accounting for the infinite relative frames of reference, because there aren't any. So basically what's easy to deduce is that the proper equation, find where A is relative to B with an variance in time from one state to the next, A star equals A plus N star minus the identity constant. And likewise, the equation for B is B star equals B minus I minus U star. So this is accounting for how in infinite relative frames of reference we have to assume and account for there being a progression, a little slight moving forward for the person or object in the more accelerated frame of reference, and then the person or object in the less accelerated frame of reference, a sort of a retrograde. So this is accounting for a slight retrograde and a slight shifting forward. What's interesting is that in special and general relativity, this is nowhere to be found, and though this is more or less accounted for with special and general relativity, this actually squeaks in right in between where special and general relativity do account for A and B experiencing relative frames of reference. And the application of this concept to special relativity reveals its relevance in the adjusted twin paradox essay I wrote in 2003, which more or less predicted the phenomena of the superluminal neutrino. In fact, I have an interesting paper trail where I was more or less contacting some people at CERN back in 2008, just before the Large Hadron Collider came online, sort of toying around with wanting to hit them up for some data, because I was looking for a particle that was moving faster than was expected based on special relativity. I wasn't necessarily expecting a particle to be going faster than light, but what's interesting about that is there's another concept that Existics fleeces out that can be applied to physics called cross symmetry. And so the neutrino, not only the superluminal behavior of the neutrino, or apparent behavior of the neutrino, I should say, not only verified my prediction I made in 2003 by applying these Existics equations to the Lorentz transformation, but it also verified another one of my more interesting concepts called cross symmetry, which we'll get into much later. So these are the basic Existics equations, and now that we've derived them, we'll go ahead and do one example. We'll graph that example and then transdelineate that into a three-dimensional time coordinate system, derive the proper vectors to then have partial derivatives that can then be plugged into special and general relativity, thus creating the vector 6, or the position 6 vector, or velocity 6 vector, which is my proposal solution to many of the anomalous behaviors in modern physics that they're finding in the lab. So this is the basics for Existics. So real quickly, these are the basic Existics equations, absent the intermediary frames of reference. One little thing I forgot to put up here real quick. Okay. So as a quick review, this is a situation where we have two individuals or objects existing in relative frames of reference, and this is within a framework that assumes that there is an infinite regress of relative frames of reference. This is a interactionism based model similar to Gottfried Leibniz view as opposed to Isaac Newton's absolute space model. So we start off with making the distinction of A being greater than B, A over B, B over A, showing them having a reciprocal relationship. Then we're going to interject in between A and B an infinite series of relative frames of reference for A. Since A is in the faster frame of reference, it's a infinite progression of relative frames of reference. For B, it's an infinite regression of relative frames of reference. So we find they're not reciprocal, but in a sense it's a reciprocal relationship because it's the reciprocal relationship, but accounting for this interconnected infinite frames of reference of A and B. So then we take these values, multiply them together, get the identity constant, which the identity constant is greater than or equal to 1. If the identity constant equals 1, then these are reciprocals, which means A and B are the same and don't require the relative frames of reference, because a single object with itself is not in an interaction with anything, so it's not subject to a model based on interactionism where you do have an infinite series of relative frames of reference following from that. So here is how we find A, where A is in the future relative to A in the present, and where B is in the past relative to B in the present. And this present, again, remember there are two events or two present moments, one present moment relative to A, one present moment relative to B. When A is in the present moment relative to A, B is in the past relative to A, then as B progresses into the present relative to B, A has progressed into the future relative to B. So the modified B is the modified B is less than or equal to B, and the modified A is greater than or equal to A. So this more or less covers the basic existics equations.